All right, so in this question you are given a memory. So let's say this is your memory that has a total size of 2 to the power 24 bytes, right? So your memory addresses goes from 0 to 2 to the power 24 roughly over here, and it is partitioned into several fixed size partitions of 65,536 bytes each, right? So recall that 65,536 is actually 2 to the power 16. Okay, so these are several partitions, and each partition has a size of 2 to the power 16 bytes. So the first question is, what is the total number of partitions, right? So the number of partitions is basically given by the memory size divided by the partition size, right? So memory size is 2 to the power 24 and partition size is 2 to the power 16. So this is basically 2 to the power 8, which is simply 256 partitions. Now the second question here is asking us how many bits are needed to address each partition uniquely. So recall that to address m different memory words or memory bytes, you need log to base 2 of m, ceiling of that number of bits, right? So here you want to address 256 partitions. So to address 256 partitions, you need log to base 2 of 256, ceiling of this number of bits. Okay, so log to base 2 of 256 is basically simply 8 bits. All right, now here is a question about translating the given C++ code into ANA assembly language. So there are two variables here, A and B. We can assume that A is in register R2 and B is in register R3. Okay, so with that assumption, let's begin this translation over here. So the first statement is integer A is equal to 10. So simply LLI R2 10, right? So this is basically equivalent to saying A is equal to 10. Similarly, to do B is equal to 1, we'll simply say LLI R3 1, right? So this is equivalent to saying B is equal to 1 because B is in R3. Now after this, let's begin the do while loop. So let's make a label do over here, and now the first statement inside this do while loop is actually two operations, right? So the first is this AND operation, and then the second operation here is the shift operation, right? So let's first do the shift operation and then we will combine it with the AND operation. So we want to do, let's say shift in let's use another register R4, and in R4 we want to shift this value of B, which is stored in R3, one position to the right, right? So recall that right shifts are negative, they are denoted by negative offset, so this is going to be -1. So this is basically same as saying R4 is equal to right shifted version of B by 1. All right, and now once we have this result in R4, we can use it to AND it with the current value of B. So let's simply say AND R3 R3 R4, right? So this is basically equivalent to saying B is equal to B and right shifted version of B by 1. So that was present in R4. Okay, and finally here the last statement in the loop is A minus minus. A, recall, is in R2, so we simply say add I R2 R2 minus 1, right? So this is basically same as saying A is equal to A minus 1. Now the last thing we have to do in this code is we need to check whether we should go back and repeat the loop starting from do statement. So to do that, we should check whether A is still greater than 0. So A is in R2, we simply use BGZ. We'll say BGZ R2. If this is correct, then simply jump to do. Okay, and the last statement here is simply halt. So the another kind of question that you might find on the exam is to convert given ANA instructions into machine code, right? So the first problem here is the LLI instruction. So for such problems, you must remember the format of the instructions. So LLI, you would recall, has this format. You have LLI, let's say R4 minus 3. So LLI, this opcode would be bits number 15 to 12. Right, bits number 11 to 9 would be your R4, and then bit number 8, recall, is unused, so we'll assume that is 0. And then bits number 7 to 0, these last 8 bits is going to be your immediate 8 value, which is -3 in this case. Okay, so the opcode for LLI is you can use the ANA handout to figure this out. So LLI is basically 0 1 1 0, R4 would be simply binary equivalent of 4 in 3 bits, which is 1 0 0. Then the next unused bit is 0. This is the unused bit. And then finally we have minus 3. So in 8 bits. So recall that 3 is given by, so 3 is given by 0 0 0 0. This is positive 3 0 0 1 1. So let's compute its 2's complement. Zeros becomes ones, ones becomes zeros, and then add a 1 to this flipped version. So the value you get is 1 0 1 1 1 1 1, right? So this is your minus 3. So that would be simply 6 ones followed by 0 1. Okay, now you cannot leave your answer like this, so you should translate this into hexadecimal. So starting from the right, groups of 4. So 1101 is D, all ones is F, 1000 is 8, 110 is 6. Okay, so this is the answer for the first instruction here. It's the same as this one. Now the second instruction is the OR instruction. Once again, recall the format. Bits number 15 to 12 is the opcode. Bits number 11 to 9 would be R5. Actually, let's do this here because there is not enough space here. So for the OR instruction, let's say you have OR R5, R4, R2. So bits number 15 to 12 is this opcode. 11 to 9 is R5. 8 to 6 is R4. 5 to 5 to 3 is your R2, and 2 to 0, these are your unused 3 bits. Okay, so this is the format. Now if you look up the ANA card, you will find that OR has an opcode of 0 0 1 1, and R5 would be the 3-bit equivalent of 5, which is 1 0 1. R4 would be 1 0 0. R2 would be 0 1 0, right? And the unused bits we assume always is all zeros. So again, to convert this into hexadecimal, so this is groups of 4 starting from the right. So this is 0, 0001 is simply 1, 1011 is B, and 11 is simply 3, right? So this is the answer, hexadecimal 3B10. Now this question is asking you to do the other way around conversion. So essentially so you're already given the machine code, and now you have to come up with the ANA instruction. So the first thing you should do is to convert this hexadecimal into binary, right? So 7 is basically 0 1 1 1, C is 1 1 0 0, A is 1 0 1 0, and 3 is 0 0 1 1. Okay, now to solve these problems, the first thing you should do is figure out what instruction you're dealing with. And remember, always in ANA, the first 4 bits of the machine code represent the opcode. Okay, so look up this opcode 0111 in the ANA card, and you'll find that this is actually opcode of LUI. Okay, now recall the format of LUI instruction. So LUI instruction is something like this. Let's say you have LUI R1, and then you have some immediate 8 value, right? So bits number 15 to 12 is your opcode, 11 to 9 is your R1. Then recall that this 8th bit is unused, so we'll assume it is 0, and then bits number 7 to 0 is this immediate 8 value. Okay, so plug in this format here. So this next 3 bits would be your destination register. This is your unused bit, and then these last 8 bits, this is your immediate 8 value. So 110 is register R6, and well, now here pay attention, because this is LUI instruction. Recall that LUI instruction is responsible only for, so if this was your 16-bit register, recall that the LUI instruction is only responsible for initializing this higher order 8 bits, right? It doesn't know anything about these lower order 8 bits. So what that means is this value that you see here, this 101000011, it only belongs to the higher order 8 bits. You don't know anything about what should go in this lower order 8 bits, and therefore if you just translate this bit pattern into a decimal equivalent, I think this comes to 93. If you simply say LUI R693, that would be a wrong answer, because you don't know what the value is. You don't have any information about the lower order 8 bits, and therefore in this case the correct way of expressing the answer is to simply express these last 8 bits as hexadecimal. So in this case, for example, 0011 is 3 and 1010 is A. Okay, so your final answer would be LUI R6 hexadecimal A3. Okay, and then the next instruction here is hexadecimal CFC1. So once again translate this into binary. So C is 1100, F is 1111, and C is again 1100, and 1 is 0001. Okay, like I said in the previous problem, the first thing you should do is figure out what instruction we are dealing with. So 1100 is actually opcode for add I. Recall that the format of add I is add I, let's say R1, R2, and then immediate 6 value, right? So this is bits number 15 to 12 is the opcode, 11 to 9 is the destination, 8 to 6 is src1, and then this final 6 bits 5 to 0 is your immediate 6 value. Okay, so this is the first register here. This is the destination register, this is src1, and this is your immediate 6 value. Okay, so 111 is basically R7, right? So this is also R7, and this immediate value is simply 1. Okay, so your instruction is add I R7 R7 1. All right, so to solve the problems on memory addressing, you again should remember the two important rules that we talked about in the class. So the first is, using n bits, we can address 2 to the power n words or bytes. This is the first rule. And the second rule is, to address m words or bytes, we need log to base 2 of m and ceiling of this number of bits. Okay, so we'll be using these two results to solve all these memory addressing problems, right? So the first problem here says that we are given an address of 39 bits, and we have to figure out how much memory can be accessed using this. So again, recall, using 39 bits, you can address 2 to the power 39 bytes, right? Because the problem tells us this is a byte addressable memory. So 2 to the power 39 is basically 2 to the power 9 multiplied by 2 to the power 30 bytes. So recall that 2 to the power 9 is 512, and 2 to the power 30 is actually giga, right? So this is 512 gigabytes. The second problem here is again as giving us a byte addressable memory, but the total size of the memory is given, it's 512 megabytes, and we need to figure out how many address bits would be needed. So now we will be using this second rule here because we are given the size of the memory. So 512 megabytes is basically 2 to the power 9, so 512 is 2 to the power 9, and mega is 2 to the power 20, so this is 2 to the power 9 into 2 to the power 20 bytes, which is 2 to the power 29 bytes. So to address 2 to the power 29 bytes, we basically need log to base 2 of 2 to the power 29 bits, right? So to address 2 to the power 29 bytes, log to base 2 of 2 to the power 29 and ceiling of this bits are needed. So which is basically 29 bits. So the third problem here, this is also a similar problem, but the difference is this is a word addressable memory where every word is 32 bits. And the question is, how much memory can be addressed or accessed if the memory addresses are 39 bits. Okay, so once again, using 39 bits, 2 to the power 39 words can be addressed. Okay, now word size is 32 divided by 8, which is simply 4 bytes or 2 square bytes. Okay, so the memory size would be the number of words multiplied by the word size. Okay, so number of words is 2 to the power 39 and the word size is 2 square from here. So this is 2 to the power 41 bytes, which is basically 2 to the power 2 multiplied by 2 to the power 40 bytes. Recall that 2 to the power 40 is actually 1 tera. Okay, so this basically becomes 2 terabyte. The fourth problem here is again presenting us with a word addressable memory, but this size, the word size is 64 bits. And the question is how many address bits would be needed if we want to address 512 megabytes of memory. Okay, so first of all, word size uh, is given by 64 divided by 8, which is simply 8 bytes, which is basically 2 cube bytes. 512 megabytes would be 2 to the power 9 multiplied by 2 to the power 20 bytes, which is 2 to the power 29 bytes. Now, how many address bits are needed? So to figure out how many address bits are needed, we first need to figure out how many words would there be in this total memory system, right? So the number of words would be given by memory size divided by word size. Okay, so that is basically memory size is 2 to the power 29 and the word size is 2 cube. So this is basically 2 to the power 26 words. So to address 2 to the power 26 words, we need log 2 base 2 of 2 to the power 26 ceiling of this number of bits. Okay, so this is basically simply 26 bits. Now this last problem on memory addressing is slightly different. So we again have a word addressable memory, but we are given the total size of the memory, and we also know, so the memory size is 2 gigabytes, and we also know that we have 28 bits in our addresses, but we don't know the word size. Okay, so let's find out the word size from here. So memory size is 2 gigabytes. So 2 gigabytes is basically 2 multiplied by 2 to the power 30 bytes, which is 2 to the power 31 bytes. Okay, now this is a word addressable memory. So using 28 bits, we can address 2 to the power 28 words. Okay, so we know the number of words, we know the memory size. So the word size would be given by memory size divided by the total number of words in the memory, right? So that is basically 2 to the power 31 bytes divided by 2 to the power 28 words. Okay, so basically this is simply 2 cube words, I'm sorry, 2 cube bytes. So that is basically 8 bytes. So this is the size of the word, 8 bytes. Alright, so this question is asking us to design a finite state machine that can detect this pattern 0 1 0 in a string of zeros and ones. So let's start by identifying the states first, right? So let's say S0 is our starting state. This is where the machine starts. Let's say S1 is the state where we have detected this first 0. Okay, this is S1. S2 is our state where we have detected the first this 0 1 pattern, right? So this pattern 0 1 has been detected at S2. So these are the three states for the machine. Now notice that all possible inputs and outputs are simply 0 and 1. So let's now go through what happens at each of these states when they get a 0 or a 1, right? So at S0, if you get a 0, this 0 might be the first 0 at the beginning of the pattern that we are interested in, right? So if we get a 0 at S0, we should transition to S1 and we should output a 0. The machine will output a 1 only when it detects this pattern 0 1 0. However, as opposed to getting 0, if you get a 1 at S0, 1 is not the beginning of this pattern that we're looking for, right? So if we get a 1, we simply stay here and output a 0. Okay, at S1 we have already received 0. So here if we get another 0, if we get another 0, you see 0 0 is not a prefix here. However, it is possible that the pattern that we are seeing is a bunch of zeros and followed by 1 0 at the end, right? So if we get a 0 here, we stay here and keep outputting a 0, waiting for the pattern. Okay, as opposed to this, we have already seen a 0, and if we get a 1, it means this might be the first 0 1, the prefix of the string that we are interested in. So if we get a 1, we should transition to S2 and output a 0. Okay, at S2 here we have already seen 0 1. So now if we see another 0, it means the pattern is complete and we should output a 1. But the question is, where should we go, right? So it is possible, if the repeating patterns are allowed, this means our patterns could be like this, right? So this is 1 0 1 0, this is another 0 1 0. So this 0, this last 0 could also be beginning of another pattern. So if we get a 0 here, we jump back to state S1 and we output a 0. Okay, as opposed to this, if we get a 1 here, we have already seen 0 1, and now if we get a 1, you see 0 1 1 is not a prefix of 0 1 0, the pattern that we are interested in. Also, this 1 cannot start a new pattern, it cannot start the next pattern because the pattern starts from 0. So if we get a 1 here, we should go back to S0 and output a 0. Okay, so this is our finite state machine. The same machine is also shown over here in a slightly different pattern. So this question now is asking us to design a finite state machine that outputs a 1 if it sees one of these two patterns. Either it sees 1100 or 1101. Okay, so let's again define the input states first. So let's say S0 is our starting state where the machine is just starting, we have not seen anything. Let's say S1 is the state where we have seen the first one in the pattern. Let's say S2 is the state where we have seen the first two ones in the pattern. And let's say S3 is the state where we have seen the first 3 bits 110 in the pattern. Okay, so this is our starting state. Let's now see what happens when we get 0 or 1 in each of these states, right? So there are again the alphabets are for input and output are just 0 and 1. So at S0, if we get a 0, you see 0 is not a prefix in either of the two patterns we're looking for, right? So if you get a 0, you stay here and keep outputting a 0. You'll output a 1 only when you either see a 1100 or 1101. Now here at S0, if you get a 1, this 1 could be the first one in the two patterns that we are interested in, right? So we transition to S1 and output a 0. At S1 here, we have already seen 1. Now here if you get a 0, you see this 1 0 is not a prefix in either of the two patterns that we are looking for, and 0 cannot start the next pattern. So we go back, if we get a 0 here, we go back to the starting state and output a 0. However, having seen a 1 at S1, if we see another one, this means this could be the 1 1 at the beginning of the patterns we are interested in. So therefore if we get a 1, we transition to S2 and output a 0. At S2 again, we have already seen 1 1. Now if we see a 0, this means 110, this could be the prefix 110 for the two patterns that we are looking for. So if you get a 0, you output a 0, but you jump to S3. However, having seen 1 1, if you get another one, well, it is possible that this is the pattern looks something like this, right? So after a bunch of ones, you have this 1100 or 1101 at the end. So if you get a 1 here, you basically stay here and wait for the pattern to unfold, right? So if you get a 1, you keep outputting 0, but you wait here, you don't go anywhere else. Now at S3, you have already seen 110, right? So if you get either a 0 or a 1, you should output 1, right? Because both patterns are of our interest. But the question is, where should you go, right? So here at 1 1, after 110, if you get a 0, you see 0 cannot start the next pattern, and therefore if you get a 0 here, you output a 1, but you go back to the starting state as 0. As opposed to this, if you get a 1, right, so this 1 could be the beginning of the next pattern of interest. So at S3, if you get a 1, you go back to S1 and you output a 1. Okay, so this is our Mealy machine of interest here.